All right, since I didn't get to it in class today, I'm going to show you this last problem out of the notes. So we've got our statement here. They tell us Cleveland is approximately 300 miles east of Chicago. Not sure if that's important yet or not. Plane leaves Chicago flying due east at 500 miles per hour. I think I can go ahead and diagram that one. So here's my plane leaving Chicago. We're flying due east, which would be to the right on typical Cartesian coordinate system, at 500 miles per hour. It says the pilot forgot to check the weather and doesn't know the wind is blowing to the south at 100 miles per hour. What is the plane's velocity relative to the ground? Okay, so that is 100 miles per hour. I think this is actually going to end up being a really, really simple question to work out here. Let's label these things because we're talking about relative velocity. So this is the velocity of the plane. It says they're flying due east at 500 miles per hour. Without context here, I'm going to assume that that is relative to the air. So I'm going to call that VPA. Okay, and this 100 miles per hour is the velocity of the air relative to the ground. So I'm going to call that VAG. Okay, and if I want to know the plane velocity relative to the ground, well, in this kind of notation, the plane's velocity of plane relative to ground. And what we remember from class today, hopefully, is that the way you would get this is you would add the two relative velocities together. So you would need one of them that starts with plane. I'm not done with this. I'm coming back. And the other one that ends with the ground, and the same object in between those, which would be the air. So as long as if we have the velocity of the plane relative to the air and the velocity of the air relative to the ground, we can get the velocity of the plane relative to the ground. So that's what I'm going to do here. Now, since these are vectors, they have direction, I'm going to have to sum these two vectors, and fortunately these are already at a 90-degree angle to one another. So really all that's left for me to do here is to just find the hypotenuse of these two. I kind of knew what was going on here when I drew this, so I tried to make it as easy and straightforward as possible for all of us. So to get the magnitude of VPG, I'm going to apply Pythagorean theorem. So a squared plus b squared equals c squared. And I'm going to want to know the c part of this, so that's going to be the square root of a squared plus b squared. So I'm going to say 500 squared plus 100 squared and square root it. All right, so the hypotenuse, which is our velocity of plane relative to ground, I should say this more carefully. This is actually just the speed. In order for it to be velocity, we also need a direction. So we're not quite done yet. So with that, I also need this angle, because I can report that as an angle, how many degrees south of east the plane is actually traveling, and that pilot may be thrown off course if no corrections are made. Okay, Okay, so let's figure that out. So we know the opposite side, we know the adjacent side of the triangle. Remember, the right angle is right there. So what I'm going to do, you could also use any other trig function you like, but I'm going to use the two original values. So I'm going to say tangent, because that's opposite of over adjacent. And that's going to be, and then to get theta, I'm going to take the inverse tangent of both sides. And make sure my calculator is in radian mode. And that will give me 11.3 degrees. Okay, so the final answer, all told, would be the velocity of the plane relative to the ground. I'm even going to throw the arrow up here to make doubly sure I know that's actually a velocity. Okay, so 11.3 degrees south of east is just telling me, okay, look east and then go 11.3 degrees south, and that is the exact direction that I am traveling. So that would be my final answer for that question. Hope that's helpful. All right, so I just realized there's another problem after the airplane problem. So we've got our skydiver jumping out, falling through there at 35 meters per second. Okay, so this is velocity of skydiver to the air equals 35. And there's a breeze blowing at 7 meters per second to the west. So that is velocity of air compared to ground equals 7 west. Okay, and what we want to know is something about the velocity of the skydiver. This may not be obvious to you, but what they're asking is respect to the vertical. What we want to know about the skydiver is the velocity of the skydiver compared to the ground. So what we just learned in the relative motion lesson was that if you want to know the skydiver relative to the ground, you could do that. If you knew skydiver relative to the air and the air relative to the ground, we would add these two together. So we're going to do VSA plus VAG equals VSG. Okay, skydiver relative to the air, air relative to the ground, and skydiver relative to the ground is what we're trying to figure out. Now, this is very much like the last problem, except it's vertical rather than horizontal. So the vertical component of this is the skydiver relative to the air, which is 35 down. And then vector addition says we'll add the tip of that vector to the tail of the next vector, which is the air relative to the ground, which is, oh, I drew it the wrong way. Okay, I drew it like it's going, usually east is to the right, so I drew it the wrong way. The angle is still going to be the same, so I'm just going to leave it. I'm not going to turn this into a mess, but yeah. So that one's going to be 7. And they asked about the angle, so I actually don't need to find oh, that's sweet. Okay. They asked about the angle, so I actually don't need to find. I was looking at part B, and it's gonna be easy. Okay. So let's take that on. So I want to know the angle. I know the opposite side from the angle and the adjacent side to the angle. Remember, the right angle is here. So tan, call it theta. Theta equals 7 over 35. And so take the inverse tangent of both sides. Theta equals inverse tangent of 7 over 35. Forgot the -1. Okay. Be right back. I think they're totally trolling me because that's exactly the same angle as last time. Must be the exact same ratio. Yeah, it's a 1:5 ratio, which is, yeah, exactly the same, 1:5 ratio. There you go. So theta equals 11.3 degrees. Now, asked when he lands, his displacement from his desired landing spot. So our skydiver, and we're totally ignoring any acceleration that took place there. So a couple of questions for you to ask. Okay, how long is he going to be in the air? That's going to be determined by the vertical motion. So we're going downward at 35 meters per second. Not accelerating, so that's constant velocity motion. So I'll do this one. XF equals, I should do Y's. I'll do the Y version of that. YF equals Y I plus VT. Okay, no acceleration here, so I'm not including the 1/2 AT squared stuff out here. And we're going from 1,000 to 0. And to make the math work here, I'm going to have to say that velocity is negative 35. Otherwise, I'll have weird stuff happen with the signs. Okay, so move the 1,000 over, negative 1,000 equals negative 35 t. And then t is going to be 1,000 divided by 35. Okay, and that is going to be 28.6. 28.6 second thrill ride there. There you go. But that's not the answer. Okay, so how long is he going to be? So that means he's going to be going 7 meters per second to the right, or to the whatever this is, to the west. For 28.6 seconds. So we're going to do our x direction this time, which is also constant velocity. Maybe I should have called that VY. Again, remember, this is because he's at constant speed, falling in a steady speed. This is terminal velocity. This is not normal this isn't projectile motion. This is horizontal and vertical, and they're both going at steady speeds, which is what a skydiver does after they get up to speed. Projectile motion would be what's happening before they get up to speed, or before air resistance is significant. Okay, so VXT. And we are going, let's say we start from 0 because he's directly over his desired landing spot when he jumps out of the plane. And Vx is 7 meters per second. And the time is 28.6 meters seconds. And that was 7 meters per second west. Okay, so when he lands, times 7, 200. And just to verify, I'm going to check and see. Yes, my answers agree with the stated answers on the notes, so that's good. All right, hope those are helpful to you.